Okay, so we start Conceptual Physics, 11th edition, on Chapter 2, Newton's First Law of Motion and Inertia. So I want to start actually by talking about Aristotle's views on motion, which he came up with in the 3rd century BC. And basically, Aristotle divided motion into two main classes, natural motion and violent motion. The idea with natural motion is that every object in the universe has some proper place determined by what it's made out of. Earth, water, air, and fire being the four elements. So any object not in its proper place will strive to get there. For example, a lump of clay being from the earth will strive to get there and it'll go down. Whereas a puff of smoke is made of air, and so it will go upwards to try to reach its natural place there. So earthly objects can either go straight up or straight down, and there was an idea that celestial objects had to move in perfect spheres. Another thing that Aristotle taught was that heavier objects, since they're made of more stuff, should strive harder to get to where they're going. So the heavier an object, the faster it should fall. So beyond Earth, motion is circular, so the sun and the moon continually circle the Earth. This is all Aristotle's ideas, and they turn out not to be right, but they're interesting. Violent motion would be produced by external pushes and pulls on objects, like a wind on a ship, or somebody shooting an arrow, or something that's not natural. So now we move way forward to the 1500s, to Italy, and Galileo Galilei, who discovered that objects of different weight fall to the ground at the same time in the absence of air resistance. So there's a little animation happening on this slide showing, I guess, Galileo up in the Leaning Tower of Pisa, dropping two objects that differ in their mass by a factor of 10, and yet they're falling at the same rate. Galileo also discovered something about inertia, and so he talked about forces being a push or a pull, and inertia being the property of matter to resist changes in motion. And this depended on the amount of matter in an object, or its mass. So this is the concept of inertial mass, which is very important. So something about inertia comes from balls rolling down or up or along a planar surface. So Galileo discovered that if he rolled a ball down a little incline, it would speed up. So its velocity would start off slow and then get faster and faster and faster as it rolled. However, if he took that same slope and tilted it upwards and rolled the ball up the hill, it slows down. So the speed starts off high and then gets slower and slower and slower. So Galileo reasoned correctly that if he had a horizontal plane and he started a ball with some initial velocity, that it should neither speed up nor slow down. So it just should have a constant velocity forever. And he reasoned, again correctly, that if the ball did come to rest on the horizontal plane, it's not due to its nature, but it's due to friction. So here we come to Newton's first law of motion, published well after Galileo died in 1687, but basically saying exactly what Galileo discovered, which is that every object either continues in a state of rest or continues with a uniform speed in a straight line unless it's acted upon by a non-zero net force. So net force. Force is a vector. So a vector is a quantity whose description requires both a magnitude and a direction. And it can be represented by an arrow drawn to scale. The length of the arrow represents the magnitude, and an arrowhead shows the direction. Force, velocity, acceleration, these are all vector quantities. So the net force is the vector sum of all the forces that are acting on an object. Example, if you pull a box with 10 newtons and a friend pulls oppositely with 5 newtons, and if you add those two vectors, 10 in one direction plus 5 newtons in the other direction, you end up with 5 newtons in the direction you're pulling. And that's the net force. Here's a block being pulled by two 5 Newton forces in the same direction. the net force in this block is 10 newtons. And here's a block being pulled by two equal and opposite forces which cancel, and the net force is 0. The equilibrium rule is about when the vector sum of forces acting on on an object equals 0. In this case, the object is not accelerated. So basically it's this. The sum, or this Greek letter sigma, capital sigma, the sum of all the forces equals 0 means that the object is not accelerating. Here's a platform, piece of wood, some guys walking on it. And there's tension force pulling up on it from these strings. There's the force of the guys pushing down on it. There's the weight of the whole plank itself. But if the sum of all the forces acting on this object is 0, then it won't accelerate. And that's the equilibrium rule. So another example, you have a bag of flour. Two forces are being applied to this bag of flour. Tension is pulling it upwards, and there's a scale reading how much tension, and weight is acting downward. That's the gravity force from the earth. If the bag of flour doesn't move, that means that the weight and the tension force must be canceling out. Okay? So when they add, they cancel to 0. So the net force on the flour is 0, and the bag of flour remains at rest. So support force. The normal force, or support force, is an upward force on an object that is opposite to the force of gravity. Example, you have a book sitting on a table. So there's a downward force of gravity on the book. That's the book's weight. And the book is sitting on the table, so it's compressing it just a little bit. The framework of atoms in the table must be getting just a little squished. And I sometimes like to think of a trampoline. If you stand in a trampoline, it squishes down a little bit. And wood is very stiff, so it doesn't push down much, but it will a little. And the reaction to it being compressed is an upward support force, or normal force. And when the book's at rest, then these two forces, normal force and the gravity force, sum to 0. So another way of understanding this is if you push down on a spring, the spring pushes up on you. Similarly, the book pushes down on the table pushes up on the book. So an object that is perfectly stationary has no net force on it, and that's called static equilibrium, like a hockey puck at rest on slippery ice. If the hockey puck is sliding at a constant speed in a straight line, this is also equilibrium, because the net force must be 0. This is called dynamic equilibrium, meaning it's moving but not accelerating. So the test to see if something is in equilibrium is whether it's changing its velocity. So a crate sitting at rest is in static equilibrium. If it's pushed at a steady speed, so the velocity is not changing, that's dynamic equilibrium. It's also net force is 0. So here's a guy pushing this crate along at a constant velocity in a straight line. So his pushing force is equal to the friction force resisting motion, and it goes along at a steady speed. Now Copernicus came up with the idea that the Earth is orbiting the Sun, and so it's moving. And many people refuted this idea, coming up with this example. If there's a tree, the bird sitting in it, and a worm down below, and the tree is moving to the right very, very quickly because the Earth is orbiting the Sun, then how could this bird dive down towards the worm and catch it without being kind of blown away or moved by the motion of the tree? Well, this idea of inertia is that the tree, the worm, and the bird all have the same constant velocity due to their own inertia, which is causing them all to orbit the Earth. So relative to the tree and to the worm, the bird just has to aim for the worm, and he'll go along at just the right path as if he was stationary.